see is happening is that we have our graph. This one's for the first one for sine. Our values go up. They come back down. They go below the x-axis. They're negative. They come back up. And we're stopping at 2 pi. But what would happen if I kept going around that unit circle? Those numbers kept getting bigger and bigger. It's just going to keep going that same amount, right? So this would keep on forever, right? So we'll even, let's draw in our line here, our graph. Make sure it's a curvy graph. It's not like a zigzag. So do the best you can in drawing that in. The points will certainly help you for that. And I'm going to put some arrows on the end showing that that is going to go on and on and on forever. I really like, let me show you this. Oh, wait, where did I put it? I put it down here. There's a link here, which obviously you can't click on your paper, but I can here so that you can see it. So let's kind of look at what's happening here. First of all, let's see, I'm going to pause this slider right here, take it back to 0. So this angle right here is my amount of radians. Notice if I go like halfway that it's 3.15. It's pretty close to 3.14. I just can't get exactly to the pi right there. So this is my angle in radians right here. And notice this x-axis is in radians because we got all those pi's right there. So if I want to watch this happen for sine, right, as my angle increases, watch that little orange piece of line right there. That tells you like your vertical displacement, your height of that point, right? Because sine is your y coordinates. So as you spin around, as you watch this point right here, just so it shows up a little there. As you watch this point right here go around the circle, its height gets higher. It maxes out right there at the top. It gets lower. Hits 0 right here. Then it goes below the x-axis, bottoms out right there. Then it goes back up. And there's one rotation from 0 all the way to 2 pi, right? So that y tells us our height as we go around. So if we continue, like if we go past 2 pi, if we keep spinning around, this same thing happens again. And this animation stops at 4 pi, but it would keep on going. We could spin around and around and around, and this would just keep happening over and over and over again, right? So those y coordinates just keep going up and down and up and down. And that's just the height of the point as it's going around the circle, right? If I take this back to 0, I'm going to cut off the 1 for sine. I'm going to cut on the 1 for cosine. Oh, that's a little weird. I don't really look at this one that much. I guess that's... Okay, so we're watching... You're watching, this blue point right here is your unit circle point. The purple point is the graph of the function, which is what was confusing me a little bit there. So as I slide this here, at first it's kind of hard to tell what's happening, but as our blue point, our unit circle point goes along this way, purple almost looks like it's tracing the circle, but as we go a little further, we'll see, no, it's not tracing the circle exactly. And then see our... Here, notice we got this little orange line right here because this is our x-coordinate, right? It's our distance from the the y-axis. And so it's going to hit 0 right there. Then over here, it's going to be the furthest from the x-axis that it's going to, from the y-axis that it's going to be. And then it goes back. It hits 0 because it's on the y-axis. Then it goes up. And then as we continue to spin around the circle, that same pattern is going to happen over and over again. For that. So this shows us how we can take these trig values and they can turn into the sine or cosine graph. And those graphs we're going to look at a lot. They're going to be really helpful for looking at different types of situations. This sort of links that together. Now let's talk about a couple things about this graph that we've got here. So this graph for sine, some important things to notice about it. I should have added this on here. Let's add it in. What is our y-intercept for this graph? Where does my graph hit the y-axis? 0. Y-intercept is at 0, 0 for that. That's important because it's going to be one of the few differences between sine and cosine. So sine right here, we need to know its domain and its range. Now, on what I have graphed right here, I went from 0 to 2 pi. But what did we say can happen if we keep spinning around and around and around the circle? Just keeps going, right? We could even spin backwards. We could go in the negative direction and it would graph the other side, right? So your domain for sine is, you can either say negative infinity to infinity, or you can say all real numbers. Or you can use the fancy R if you want. So we can plug any number into sine or cosine, and we can get an answer from it. If you think of it, especially thinking in degrees is a little bit easier for me. Like, I can plug any number in because it's just a number of rotations. Like, if I plug in 360, it's 1 rotation. But I could plug in 720, that would be 2 rotations, right? It's just, you know, I could plug in 1 million, and it's going to be a whole bunch of rotations before it finally gets there. So the range, however, is restricted here. If we're thinking about our y values, what is the very lowest that our y could ever be? -1. So we're gonna use a bracket because it can equal -1, so we want to use a bracket there. What's the highest that is ever going to be? +1. All right. You also might see this written -1 less than or equal to y less than or equal to +1. Okay, questions here? All right. Cosine function looks a lot the same, right? What you should see with the cosine function is that it's going to have pretty much the same pattern, but its y-intercept is going to be different. So I'm guilty of calling it the starting point a lot of times. I don't guess sine really has a starting point. It's your y-intercept. But the y-intercept here is at a maximum for cosine, whereas it was at 0, 0 for sine. But if you look at these two graphs together, like if I go over here to Desmos and I turn both of these on, they look a lot the same. It's just one of them starts in a different position. They're kind of slid over from each other. Let's add in y-intercept here. For cosine, my y-intercept is 0, 1. And is there going to be any difference in the domain from sine? How about the range? Also the same, right? Still highest is +1, lowest is -1. So this is the same as it is for cosine. Your domain is from -infinity to infinity, or you could just say all real numbers. I'm going to use the fancy R there. Or your cosine is -1 to 1, or you might see it written as -1 less than or equal to y less than or equal to 1. Now, when you guys take your quiz on Friday, I'm going to go ahead and show you the question that you'll see. When you take your quiz on Friday, here, oh gosh, I'm in the wrong class. What did I do? Why is it so slow? Okay, so Thursday's just unit circle. On Friday, whenever you take this quiz, no, not that one, the using the unit circle quiz, oh wait, I don't need to edit that. Let's do preview. I'm going to show you the first two questions exactly right now. No, never mind. Oh, this isn't Friday's quiz. This is the quiz next week, but I'm going to go ahead and still show you that, even though that's far in advance. This quiz, just to point out how important this is. When you take the quiz next week, the first question, this is definitely, everybody's going to have the same question for the first two. The first one is going to say, which of the following is the graph of y equals sine x? And so you have to just pick which one is sine x. And it would be this one, because it starts at 0, 0, and it goes up, and then it goes down, right? Then the second question is going to be which one is the graph of cosine x. And so the graph of cosine x is going to be this one. It's going to start at a maximum point, and it'll go down and then back up, all right? So those should be easy problems for you, because if you don't know how to do those, if you don't know what the sine and cosine graphs look like to start with, when we do the transformations, you're going to have a really hard time for that. So make sure that you know what these graphs look like here and are able to produce those easily. So now we have an activity that we're going to try. And let me go over here. I'm going to pass out a paper for you. So, for this activity, we're going to do a jigsaw activity. And this has a couple purposes. Number one, I think it's kind of a good way to do this. Number two, I'm enrolled in some sort of research thing from Appalachian where we have to do these micro-credentials where you try these strategies in your class, and it's like professional development for teachers. So anyway, jigsaw is one of the ones that I'm doing. So you guys are also my experiments right here. So that's one reason, but I do think it hopefully is going to work pretty well for this, because you should have a little bit of familiarity with this anyway. The way this will work is I have assigned all of you, although we are going to have a little bit of trouble because Ethan is not here. I knew Maggie was not going to be here, so I didn't assign her one. But Ethan is not here, so I might just have to be Ethan for that group, or at least to help out your general group. So the way jigsaw activity works is you have an expert group, and then you have a general group that you're going to go to. So in a moment, we're going to split into our expert group. So I am not really going to teach you this with notes like I normally do. We are going to go to our expert group, and Maddie and Anaya are going to work on period and frequency. They actually have two right there, but those are related, so they should be pretty easy to do together. Granger and Alyssa are going to be my experts on amplitude. They're going to be able to explain it. Midline experts here, concavity, and even odd expert here. So what you are going to do for me in your expert group, I have made a set of notes for our class, but they're mostly blank. You'll make sure you click on the one for second period, not the one for third period, or you'll be putting it in the wrong place. So that's just which section we're looking at. And then I did go ahead and do this definition for us. A sinusoidal function is any function that involves additive or multiplicative transformations of f of theta equals sine theta. So it is any transformation of the graph of sine. Notice cosine is still a sinusoidal function, because cosine is really just the sine function that's been shifted over, right? Because if we look at, I still have that Desmos pulled up. If we look at this graph, this green graph is my sine function. If I just slide it this way, pi over 2, then it matches up with my cosine graph. So what we're going to see for the most part is when we're dealing with sinusoidal functions, we use sine a lot of the time, but cosine is also technically a sinusoidal function. For what you're doing here, you're mostly going to work on sine today. Like if you are an expert on amplitude, you're going to go to the slide that says amplitude, and I put the title there. You're going to provide a definition and a visual representation for what amplitude of a function is, right? You are welcome to, what I would suggest, you can, the internet is fine. You can, especially for visuals, if you want to pull some pictures there. You also could just use Desmos if you would like, depending on what you're having to show. You can Google stuff. I would suggest, I added here on our stuff for today. Where is it? I added this right here. It's AP. It says AP underneath this jigsaw activity. It says AP Pre-Calculus course and exam description. If you click on this and click open a new window, if you go to section 3.5, which is going to be way on down here, let's go. If you go on down here to 3.5, right here, it's going to have a lot of the essential knowledge here sort of gives you the definition for some of those. I would suggest using this first. Some of it doesn't give you a definition. Some of it you may have to go look up a definition. But these are the things AP says we're supposed to learn in this section. So it's going to be worded most like you're going to see on a assessment. So I would start from here, and then if you need to Google to fill in or get your visuals or something, you can there. So the first thing you're going to do is you're going to add this to your slide. Please do be careful because everybody has editing rights. So please don't delete stuff other people have done. Make sure you're doing that. So the first thing you're going to do is you're going to add this to the notes. Then, this hopefully is only going to take us maybe 10 minutes or so. These are just little pieces of information that shouldn't take too long. Then, what you're going to do is after everybody has got this part done, we're going to split back up into our general groups. So what should happen is everybody is also assigned to a general group. Let me go back over here. So there should be 5 of you in your general group, except for you guys. I'll have to be the 5th person here. So in your general group, you should have one person that's the expert on everything. So if you're talking about amplitude, you just worry about amplitude. Don't worry about what the period or the concavity or anything else is. Just amplitude is all you're worried about. And then when you go to your general group, that worksheet that I just gave you at the bottom is asking you to label a few things and give the sign, the period, the amplitude, all of that for the sign function. So you'll work together to fill that out because you should have one person from each expert group to help you answer those questions. Okay, does that make sense? All right, so go ahead to your partner that is your expert partner. So go there first. And Emma, if you need any help, I'll help you out a little bit because you are alone for that.